Hello and welcome back once again. So, we have started discussing about the strengthening mechanisms in metal matrix composites.
Okay, so with regard to the dislocation mechanisms of strengthening in MMCs, we talked about the Orowan mechanism, which says that the dislocations bend around the particles, and while bending around and leaving the particles, dislocation loops will be left behind, and that will actually hinder the motion of other dislocations which will encounter the particles. Okay, and that is how the strength will increase. And then we also talked about another mechanism which is the grain size strengthening. Since the particles can act as the nucleation sites, they can refine the grain size, and that will give rise to a higher strength. Okay. Now let us move to the other dislocation mechanisms with regard to the strengthening in MMCs. The next one talks about work hardening, as to how the work hardening can occur in a composite material and how it can give rise to strengthening. So what happens during plastic deformation? The unreinforced alloy generally exhibits a gradual increase in the yield strength. And this is connected with the long range dislocation glide. We know that plastic deformation in metals takes place by dislocation motion. So the yielding which occurs in the matrix in this case is connected to the long range motion of dislocations. And now you have to look at the scenario when the particles or the reinforcement phase is present, as to what will happen to this yielding and how the material will strain harden when there is a presence of a second phase, which is the reinforcement. Okay. So the presence of the reinforcement will cause interruption to the material flow, because the reinforcement is much stronger compared to the matrix. So when the matrix is yielding or deforming plastically, the reinforcement can still be in the elastic condition, and as a result of that, it will actually interrupt the material flow which is occurring in the matrix. Okay, and this will lead to generation of dislocations. And dislocation tangles can form around the particles at low strain due to this plastic incompatibility between the reinforcement and the matrix. So as the deformation continues, geometrically necessary dislocations known as GNDs in short will be generated at higher strengths to maintain the continuity. And therefore, the work hardening will increase. Through those forest hardening kind of mechanism, which comes into picture when the dislocation density increases. So here, as more and more dislocations are generated at higher strengths, the dislocation density will increase in the matrix, and this will lead to forest hardening and result in increase in the strength of the material. And this was explained with the model by Ashby. The Ashby model talks about the misfit strain and the associated strengthening due to that, due to the generation of additional dislocations because of the misfit or the plastic incompatibility between the matrix and the reinforcement. Okay, so let us have a look at this model as to how it explains that particular phenomenon. So it considers a hard particle embedded in a matrix. And let us consider a spherical particle. And let's say this matrix particle system is loaded in tension in a particular direction. So let's say it is loaded along this particular direction. So this tensile loading in this particular direction will also result in a homogeneous shear strain along x1. And the particle would tend to deform to an ellipsoid as the load is applied and the shear strain is developed. With the longer axis along the loading direction. So this was the loading direction along this. So it will become an ellipsoid shape along the loading direction. Right, so from a circular shape, it tends to become an ellipsoid along the loading direction, as shown schematically by this diagram here. And now if you try to remove the particles without removing the load, then it will tend to become more elongated. And in order to pull it back towards the original spherical shape, then certain amount of displacement will have to be applied along these two directions, as you could see by these arrows over here. So certain amount of displacement along this direction and along this direction also has to be applied. And this is equivalent to punching out of dislocations from the interface, from the particle matrix interface. And this will happen along four directions, as you could see from here. And it can be shown by another diagram like this. So this represents punching out of dislocations, like what we discussed before. The plastic incompatibility or the misfit strain which is generated due to that leads to generation of the geometrically necessary dislocations or GNDs. Okay, so that is what is being represented over here, and this will lead to an increase in the dislocation density, and the forest hardening mechanism will come into play due to that, and as a result of that, the strength of the material will increase. There is one more factor which leads to generation of additional dislocations in a metal matrix composite, and that is the difference in the thermal expansion between the matrix and the reinforcement. So the thermal expansion coefficients of the matrix and the reinforcement are different, and due to that difference, misfit strains will be generated, leading to generation of additional dislocations. So this strain will be generated near the interface between the matrix and the reinforcement. So if you look the microstructure of any metal matrix composite closely and observe the interface, you would always find a high dislocation density near the interface. And as you go away from the interface, the dislocation density will decrease. So this is because of the fact that near the interface, the misfit strains are generated due to a difference in the CTE between the particle and the matrix. Okay. So this was also explained with the help of a model which we are going to talk about right now. So this model talks about punching out of dislocations from the interface. The mechanism goes by the name CTE mismatch mechanism, and the model which is proposed to explain it is known as the punching model, which basically talks about punching out of dislocations from the particle matrix interfaces due to a difference in the CTE that leads to generation of misfit strain. So this model was proposed by Arsenault and Shi. And they considered equiaxed particles in a metallic matrix, and the dimensions of the equiaxed particles are given as T1, T2 and T3. So this is the particle which is considered over here. and these are the dimensions of the particle. So what this theory of the model says is that because of the thermal stresses which are generated due to the CT mismatch, dislocations will be punched out from the interface. So these slices that you see over here, these represent the punched dislocations. Right, so that's how, as I said before, if you look at closely the particle near the interface, you would see that the dislocation density close to the interface will be higher, okay, because due to these thermal stresses, dislocations will be generated from the particle matrix interface. And the strengthening due to this thermal mismatch is given as follows. Where rho is the dislocation density and alpha is a constant having a value between 0.5 and 1. And the dislocation density rho will depend on the thermal stress generated due to the difference in the CTE and the particle size. Where dp here is the particle size and fp is the volume fraction of particles, and the thermal mismatch is given by this delta beta. And delta T, of course, is the temperature difference, right? So when you cool down the composite material from high temperature to a lower temperature, due to this CTE mismatch, thermal stresses will be generated, okay? So during heating and cooling of composites, thermal stresses can be generated due to the mismatch in the coefficient of thermal expansion between the reinforcement and the matrix, and that would lead to generation of dislocations, and the matrix will contain higher dislocation density, which is given by this expression over here, and that would in turn lead to a higher strength according to this particular equation, okay? So these are the different dislocation mechanisms of strengthening in a metal matrix composite. So before we finish this lecture, let us summarize it. So in this lecture, we talked about the dislocation mechanisms of strengthening in metal matrix composites. There are different mechanisms which operate in a metal matrix composite and give rise to a higher strength. Orowan strengthening talks about the bypassing or bending around of dislocations around solid impenetrable particles, and this leaves behind dislocation loops which make it difficult for the other dislocations to pass through the particles, and as a result the strength of the material increases. The presence of the particles also gives rise to a finer grain size because the particles can act as nucleation sites and increase the nucleation rate and hence producing a fine-grained structure. Okay, and therefore the strengthening contribution can come from the grain refinement also as per the Hall-Page relationship. And then we talked about the work hardening strengthening mechanism, which basically arises due to generation of dislocations because of the plastic incompatibility, which leads to misfit strains, generating more dislocations in the matrix and leading to a higher work hardening, which leads to an increase in the strength of the material. Then we also talked about the strengthening due to thermal mismatch arising out of the mismatch in the thermal expansion coefficient between the matrix and the reinforcement. So because of this mismatch, misfit strains are generated at the interface between the reinforcement and the matrix, and as a result of that, dislocations are generated, and this was explained with a model by Arsenault and Shi, who considered these particles to be equiaxed and shown that dislocations can be punched out from the interface due to the misfit strain, and this will increase the dislocation density in the matrix, leading to a higher strength according to this equation, where rho is the dislocation density. And this dislocation density is dependent on the thermal mismatch, as you could see from this particular equation, right? So because there is a difference in the CTE during heating or cooling of the composite, thermal stresses will be generated in the composite and it will generate dislocations in the matrix, leading to a higher dislocation density, which will give rise to a higher strength. Dislocations can also be generated due to the plastic incompatibility between the particles and the matrix. When the composite is loaded, the matrix will yield, but since these particles are stronger, the material flow will be interrupted, leading to generation of additional dislocations. So this will also increase the dislocation density, and the strength will increase by the forest hardening kind of mechanisms, which talks about interaction of the dislocations on the slip plane with the additional dislocations which may be generated in the matrix.
And with that, we come to the end of this lecture. Thank you for your attention.